And the first talk of this session is by Asaf Ter, who will be talking about spectrophotophotospheric emission on gamma reverse spectrum.
All right, thanks very much, Yuri. Is everybody ready? So effects of photospheric emission gamma reverse spectrum basically works by myself and June3, my main collaborator here, and other people that contributed. Well, Myers, Peter Nazaros, Martin Rees, Bing Zhang was the recent one. It's kind of summary of 4 recent papers that will appear also on the last slide. So we'll go over it. What I want to say. First, well, I was happy to have like introduction, advertisement last time, yesterday by Felix. So I'll give like a really brief review of what I think are the key results that Felix found. Which is basically saying that when you look at the prompt emission spectrum of gamma ray burst, you are seeing evidence for a thermal component atop the overall non-thermal part of the spectrum in zero bits. And the important part is that there is a characteristic behavior, temporal behavior, of both the temperature and flux of the black body component at late times. And then I'll start by guiding through the physics of what I find really fascinating physics of the theory of how we can understand temporal behavior. In one sentence, it will be highlighted emission in optically thick expanding plasma, so which is somewhat very different than what many people, at least in the gamma ray burst community, are used to as highlighted emission from optically thin plasma. I'll go through that in some more details. And the most interesting, I think, if you accept all this picture, is the implications. As Felix already mentioned yesterday in his talk, thermal emission, in a sense, is much simpler to understand than the non-thermal one, and it can give us a whole lot of insight into the physics of these outflows in gamma ray bursts, and in fact also in other objects in which it could be identified. So I will speak about currently 3 implications we have, and it's really an ongoing research, so there will be more next year, etc. And people are welcome to join. So the 3 things that I'm going to speak about will be just a few words on analysis of the spectra. What's the relation between the thermal component and the non-thermal one? And it's really non-trivial relation. And then there is a work that we did a couple of years ago about showing how we can use this thermal emission to have a direct measurement of the hydrodynamical properties of the outflow, in particular the Lorentz factor gamma and the flow radius R0. And the last thing is the last work that just published last month with Bing, which is kind of a long shot, but I think it's very interesting, showing that when you look at thermal component, you might even be able to say something about the composition of the GRB outflow, which I think is pretty interesting. So let's go really briefly over what Felix was showing. What Felix was doing basically was taking this spectrum, complex spectrum of prompt emission of various bursts, cut it into time bins, and in every time bin identify the thermal component and the non-thermal one, and looking what is the temporal behavior of this thermal component. And this shows you the temperature, and the amazing or the really interesting part is this repetitive behavior that is being seen in many different bursts. Seems to be roughly constant for several seconds, and then seems to decrease, and the decrease is as a power law in time. So this is time scale of a few seconds, and this is temperature, canonical value of say about 100 keV, and then it drops with some state power law, which is about minus 0.7 roughly. And this behavior seems to repeat itself, as Felix was saying, in many different bursts, some of which thermal component dominates, some other in which thermal component does not dominate, but it can be still identified. So that's about the temperature. Flux, again, seems to do the same thing. Broken power law behavior, well characteristic indices, early times and late times. Break time is, not surprisingly, within the same errors as the break times in temperature. And the late time behavior goes to the -2. And we did this analysis on a fairly large sample of bursts. This is so far 56 bursts. Simply, we stopped there just because we said, okay, that's enough to make a point here. But this is ongoing, so you can just continue on doing that. And this is the histogram of the spectral breaks. So that's the power law indices after the break time. So temperature goes roughly as -2/3. There is some spreading here, and flux drops as roughly t to the -2. Again, there is some spreading, but there's a general picture that emerges. I find this really fascinating, the fact that you see this repetitive behavior. That by itself, I think, from a theoretician's eye, that means that may worth looking at it and seeing if there is really something in it or it's just a complete coincidence. So just before I go to the theoretical perspective, there is another parameter also Felix mentioned that in his talk yesterday. This is simply the ratio, taking the flux divided by sigma t to the 4. You got the dimensionless number, take it to the power 1/2, and that dimensionless number is somehow related to the photospheric radius. And that's how it evolves, and the scaling is not very at the same time, and you're seeing that it's roughly slightly increasing with some t to the power beta. Beta is around, say, 1/2. So we'll get into that in the next part of the talk. So as I said, from a theoretician's eyes, this is pretty interesting result. There might be something in it. And again, Felix also mentioned that in his talk yesterday, you actually, in most models of GRB problem, you actually expect to have thermal photons. And I just want, just from completely simplified arguments, not really getting into the details of what happens here. If you take the fireball model, but also alternative models, generally, if you just look at the energy, where's the energy? You have two episodes of energy conversion. One would be from the gravitational energy or the explosion energy converted into kinetic energy. We heard these talks yesterday, for example, by Miguel, of how jets are formed, basically, right? And then there is a second conversion of energy in which the kinetic energy is being converted to radiation, which is what we're seeing, right? And that was the talks also today by Peter and others that mentioned that this is it's not exactly clear how it's done. Even if standard models will say internal shocks, but it's well known that these are really inefficient. The point is that you can have two sources of thermal photons. One would be if this conversion occurs pretty deep in the flow when the optical depth is high, so below the photosphere, so the photons will have, regardless of what exactly produces them, will have enough time to thermalize. But there is also a second source of thermal photons, which will be related to this first conversion. So somewhere over here, the classical fireball model will tell you that the mediator of this transition will be through photons. So the photons would actually push the jet. And so whatever you have there, which will not be converted, any energy that will not be converted into kinetic energy will eventually, neglecting, of course, neutrinos and gravitational waves, etc., other things, but will end up as photons which will have sufficient optical depth to thermalize before escaping. And interestingly, if you take the simplified model, you have a very simple relation of where is the photospheric radius, the radius at which the optical depth equals to unity, as a function of the luminosity and the Lorentz factor of the flow. Those equal values will give around 10 to the 12, 10 to the 13 centimeters. So we know, or we're supposed to know, where is the emission radius of the thermal component. Again, in a very simplified model. But now things become, more interesting. And when you start to think, okay, can we quantify this thermal emission? Then you realize that it's not that easy as it may sound from, first place. And I like this cartoon because it's a fairly simple one to understand, I think, and it tells you a whole lot. What this cartoon tells you is, let's assume that the observer is located somewhere over here, and it looks at two photons that are emitted at the same radius, and tries to get into it. And these two photons are, propagating in a relativistically expanding medium. So you have, say, electrons, scatterers that are expanding. And say, if you want to calculate the optical depths, or photospheric radius in which the optical depth equals to unity, for this photon, you basically have to integrate over the optical path, right, of this photon from its emission radius to the observer, which is somewhere over here. Just by looking at that plot, you can imagine that these two photons, although emitted at the same radius, you see a very different density profile from the way to us. As a result, the optical paths would be very different. And so if, say, the optical depth to this photon from this, say, radius r to us is exactly unity, then this photon will see a much higher optical depth. In other words, what I'm saying here is that the photospheric radius strongly depends on the angle to the line of sight. Okay? Now, fortunately, this problem was treated already, 18 years ago by Abramovich, Lubko, and Kuczynski, not in this context. So that was a good starting point, which you could continue from there. And when you continue from there, which I did, then you find out that the photospheric radius is a function of the angle to the line of sight theta can be put in a amazingly simple form, which is some constant which depends on the parameter of the outflow, particular m dot, which by itself depends on the luminosity and the Lorentz factor of the electron. And then as a function of angle, it's just theta over sine theta minus beta. That is the velocity of the electrons, relativistic electrons. For smaller angle to the line of sight and higher Lorentz factor, this is discussed in even simpler form, which just goes 1 over gamma square plus theta square over 3. Which means, this is what is plotted here. So for angle to the line of sight theta, which is smaller than 1 over gamma, that means photospheric radius is constant. And for higher angles, it goes theta square. Well, so this is for two values of the Lorentz factor. The first thing that this nice calculation gives us is the correct time scale. Correct time scale meaning, okay, let's say that you have two photons. One is both of them are emitted from the photosphere, but one is emitted, say, on the line of sight, and the other is emitted from some higher angle to the line of sight. And the first question you'd ask is, okay, what's the time delay between these two photons? Classically, you would say, okay, this is r over gamma square c, so it's not really, it shouldn't be really a big time difference if you're speaking about photospheric radius, which is about 10 to the 12. But when you do it correctly and you enter this geometrical factor, you get for plausible values relevant for gamma reverse, like luminosity of 1052 ergs per second, Lorentz factor of 100, and say angles of about 0.1 radian, or 5 degrees, you get orders of tens of seconds. So the first thing it does, it brings us to the correct time scale that we're observing. That's the same time scale that we're seeing. So that's already, pretty encouraging. But we're really interested in calculating the flux, and the evolution of the flux and the evolution of the temperature. And for doing that, when you think a little bit deeper of on that problem, you find out that just looking at the emission from the photosphere, which is again plotted here, it's this green line, is simply not enough. Because photons have, finite probability of being scattered at every point in space in which they are scatterers, i.e. electrons, and that means every point in space in general. This just gives you the probability where it's exactly optical, it's exactly unity. But, this is the result of a Monte Carlo simulation that I built. It basically shows you the last scattering positions in space of these photons that are, say, being introduced into the flow deep inside in the flow, and then they're just being scattered until they escape the flow somewhere close to the photosphere. And as you can see from here, there is a large distribution, as one may expect, and these distributions are correlated in theta and r. But what you can do is that, of course, you can solve it numerically. What would be more interesting to try to solve it analytically. And actually, this can be done under some approximations. And in order to do that, what you have to do is to introduce probability density functions of what is the probability of photon to have last scattering event radius r and angle theta. And once you have these probability density functions, then you can calculate what would be the observed flux simply by integrating over all space under the delta function approximation in time, which basically, again, let's say that the physical picture that you have in mind is the following. You have all the photons are introduced very deep in the flow, and then they're advected with the flow, and so their velocity component in the direction of the flow is theta c, and then at the last scattering point they are being scattered to the observer, and so the observed time is just related to the r times 1 minus beta cosine theta divided by beta c. And then you integrate over all the arrival times, equal arrival times of the photon, which are these dotted lines. And what you find is the flux, of course, integrate over the probability of a photon to be last scattered at radius r and angle theta. And what you find is that at late times this goes to the minus 2. So that's basically is equivalent to solving the diffusion equation in relativistically expanding plasma. Okay, and that gives you that the flux at late times should decay as t to the minus 2. Which is quite interesting. Because again, it's very similar to what we've seen and what Felix was showing. The second thing that we are interested in calculating is the temperature decay. Again, we have this passive observation. And in order to do that, we need to know the temperature of a photon that we're seeing, or the energy of a photon that we're seeing, depends on two things: on its co-moving energy and on the Doppler factor. Doppler factor we know because we know what is the last scattering angle. So the interesting thing is to know how the co-moving temperature drops as a function of time. What you have is a mechanism that is kind of cousin of the adiabatic energy losses. It's not exactly the same. I don't have too much time to get into the details of it. I just say that when you think of the microphysics, because there's no like general co-moving frames, there's only local co-moving frames, because the electrons, the scatterers, velocity profile is different for every electron. And so, for example, if you take the Thomson regime, in which electron does not change its, a photon does not change its energy in a scattering, still after the scattering, the photon will see all the other electrons receding away from it. End result would be that the co-moving energy of a photon, local co-moving energy of a photon drops r to minus 2 beta over 2 its first direction. Again, that's kind of a cousin of classical adiabatic energy losses. When you plug it in, you end up, again, with a similar integral, you end up with something that is pretty close to minus 2/3. Something between t to minus 2/3 and t to minus half. And when you take the ratio f over t to the 4 power 1/2, you get something that increases in time, roughly as t to the third to t to the power 0. That's pretty fortunate because, just to remind you, histographs gives you exactly that. Observed time on the average roughly is to the minus 2/3. Flux decays on the average is to the minus 2. And so the predictions of the theoretical model of this photon diffusion from below the photosphere seems to be in very good agreement with the observational results, which for me is another indication that probably we're doing something right here. Again, you cannot say it's a proof that there is thermal emission photons, but the fact that you get it, the fact that you see the repetition, the fact that you get good agreement between theory and observations, for me it's encouraging. Now, let's go to we got 10 more minutes, so let's go to the next part, which is implications of that. So I said I'm going to really briefly speak about three implications. This is a relatively old one already. It was done in 2006. What we did here, it was a work done with Peter Rosaros and Martin Rees. What we did here was, assuming that there is some dissipation, without saying what it is, that produces energetic electrons into an outflow in the vicinity of a large or significant thermal component. Now what happens, briefly, the physical picture I'll try to show you that the electrons tend to thermalize much quicker than the photons, simply because they undergo much more scattering than the photon undergo. And then what you're seeing is the result of a complex spectrum in which the main emission mechanism would be comptonization of the thermal photons. And so, the spectrum width depends on the parameters that you put in. Important part, there are several really interesting parts in this figure. For example, the fact that for optical depth, which is around 1,000, you get nearly full thermalization or wind spectrum. For lower optical depths, which is order of a few, which is roughly what we expect, so what the thermal shocks may be, you get flat spectrum above the thermal peak. For lower ones, you can see the thermal peak, and then there is an extra components coming for comptonization. The bottom line here is that the spectrum could be pretty complex. It's not just a simple broken power law that one may expect when the optical depth is very low, for example, as in the optical. There's a lot of back reactions here, there's a lot of interaction between electrons and photons. So if you really want to model the spectrum, it's not that easy. That's the point I'm trying to make here. If you want, maybe we could have some more discussions next week about it. And since then, there are also other works, other people doing some works on that. Giannis was doing some work, Tayoko was doing some work. And again, the spectrum could be pretty complex. The second thing I want to say, which I find really amusing, I would say, is that you can actually use it to say something about the hydrodynamical properties of the outflow. In particular, when you look at the observed flux, it's just integrated over the emitting surface of the intensity. When the intensity of thermal emission is just sigma t prime to the 4 times there is a Doppler factor to the 4 power. When you look at the ratio of these, what you get is just something which is proportional, with proportionality constant, the order of unity, it doesn't really matter, to the photospheric radius divided by the luminosity distance, provided you know what it is. And there is an extra factor of gamma, which is basically effective transfer size due to relativistic aberration. So you have to introduce it here. Once you have that, let's see what you have. We have basically three knowns. We know the observed flux, we know the observed temperature, and let's assume we know the observed redshift, for example, in this case. The point here is that we are assuming that if this is due to, the late time is due to this extended high latitude emission, that means at early times, the spectrum is dominated by photons emitted on the line of sight. Okay, so we know that how the photospheric radius on the line of sight depends on the parameters. So we have three knowns. There are three things that we can tell that we are searching for, which is the total isotropic luminosity, knowing the flux, and we know what it is, right? 4 pi minus distance squared times flux. And then there are other two, which is the Lorentz factor and the photospheric radius. And this is simple, matter of simple algebra. The R is just portion of the photospheric radius divided by gamma. The spheric radius factor of L and gamma. So you can write it as L over gamma, and then we can get the whole on what is gamma, and again on the photospheric radius, which is quite nice. And now, in principle, the photospheric radius is the innermost radius in which you can get any electromagnetic signal coming to us, right? Other signals like neutrinos can come from earlier points, but not electromagnetic signals. So if you want to say something about what happens from below the photosphere, we need to have a model. Now, fortunately, we do have a model, which is a classical fireball model. People like Paczynski, Piran, Nezeros, and others work on that. And that tells us how the temperature of the photons should evolve from below the photosphere. So if we trust the model, then it says that the jet starts to accelerate with some inner radius R0, which is the size of the base of the flow, and then it accelerates until it coasts, saturates, and then there's photospheric radius. There are some technicalities involved here, but we'll leave them. The point here is that we can say something about R0, the size of the base of the flow. Why do I think it's very interesting? The reason I think it's very interesting is because I believe that R0 is somehow related to the mass of the progenitor. Let's say R0 would be the sonic point, so it would be somehow directly related to the mass, and gamma would be related to m dot. So I think in the future work we might be able to say something about that, but currently we're not saying anything. We just say that we can measure R0 and gamma, and we actually did that for this particular example, and find gamma of 300. The important thing here is that the statistical error bars that we can get are 10%. This is way better than any other method of measurement, although there are some systematics here, mainly related to the fact that we need to know what is the total luminosity in the non-trivial component. But still, I think statistical error was 10% really good for that. The last point I want to make, this first has already been discussed by Peter Mazaros and others, the Fermi observation of the 080916C. Briefly, very energetic burst. And the important point here is that there were 13 GeV photons that were seen, and it has a great spectral coverage, over 6 or 7 orders of magnitude. And the fit was done to really good fit to length functions. In other words, there were no thermal emissions in this burst. So you can say, oh, well, why are you showing this? This just kind of ruled out everything you say. Let's say no. I mean, let's see. If you go on through the same reasoning, let's see what you can say about this thing. And apparently, you can say quite a lot. So this is the work that I did with Bing. See, the fact that you are seeing 13 GeV photons just from compactness arguments that were already noted in the science paper gives you some limitations on the emission radius of these photons. It should be between 10, 15, and 17 centimeters. These are the 5 lines here corresponding to the 5 epochs that we're seeing. So the emission radius of these photons must come out from these lines or above. These dotted lines are what you'd get if you trust, say, another relation between the emission radius and gamma. For example, in the internal shocks model, you're saying R is gamma squared C delta T. So for given delta T, these points, and then you tell, okay, gamma should be about 1,000. We release this argument. We just say, okay, let's put gamma into 3 parameter, and for plausible values of gamma, you'd get emission radius of say 10 to 15 to 10 to 17. This is about the photosphere. The photospheric radius is plotted here, you can calculate it, and you get some value which is about 10 to 13 to 10 to 15. So clearly, these 13 GeV photons are not from the photosphere, and that's what I'm saying here. Okay, fairly simple. But then, okay, where's the photosphere? where's the photospheric emission? Now, if you trust what I say, the classical fireball model in which the acceleration is mediated by the photon, then you should see a clear signature of these thermal photons. And you can calculate what you'd expect to see. And what you expect to see is calculated over here, which is clearly not seen, right? These are the fits. And so, just to be on the safe side, I did ask Felix to search for it, if you can see something. That's the result. So there is a very weak thermal component, which is in about the same temperature as you'd expect it to be, but it's much weaker, significantly by a factor of about 20 than what you expect. So the conclusion that we draw from that is that somewhere in between the photospheric radius and the actual emission radius, there is an excess of energy by a large factor of about 20. This is what we expect to see. These are different models. Again, we don't know exactly what is gamma, or if we don't want to, so if we don't trust this, and we say, okay, gamma is 3 per meter, then there should be some excess of energy. Now that's what we said, and of course, given no other good source of energy that we can think of, then it's most plausibly due to magnetic reconnection or some other, magnetic effects that produces this energy somewhere in between photospheric radius and the emission radius. And then, that connects to the other talk that we had already, talked by Miguel about acceleration, talked by Anatoly about the fact that in this case, most probably what you're seeing here is not due to internal shocks because we are inefficient in the magnetized plasma, talked by Dimitrios that will follow. And so I think, if you go with this line of reasoning, you get a pretty interesting result. That led me to the last slide, the summary slide. So what I want you to take really out of this stuff. So first, I start by summarizing what Felix said in his talk, and I think this is a very key point, especially to the observers in the crowd. I think when you look at the quantum emission, there is by now evidence for thermal component. Again, we're not the first to say that. For example, Giancarlo, which is sitting here, already said that in his analysis in 2003. Felix said that in his talk in his analysis 2004, 2005. And there is an analysis which kind of comprehensive one, I think really shows that. And so in any analysis that you do to the Fermi data, I think you should look for it, and I think that it's highly likely that you find it if you really look for it. And then what I tell you is that the temporal evolution, which is very well defined as shown by Felix, can be explained by this model of extended high latitude emission, extended emission from higher angles and higher radii at later times. And that gives you a very good, agreement between theory and observations. And then what I said is that there is a connection which is non-trivial connection between thermal emission and the non-thermal part of the spectrum. So if you really want to understand the non-thermal, not just saying, okay, that's a non-thermal, but really understand what is the physical mechanisms that are involved, you do need to do this analysis right. You need to identify the thermal emission, saying, okay, how significant it is in, say, electron schooling, and whether what we're seeing is synchrotron or maybe just comptonization of the thermal component. And then what I said is that when you make observations at early time, if you're able to identify it correctly, thermal emission, and you cross all those what you think, that will give you a direct measurement of the hydrodynamical properties of the outflow, Lorentz factor gamma and size of the base of the flow are not. And when I continue on, I said that if you trust all this, then the non-detection of thermal emission in this particular burst, 08, 09, 16C, which was already discussed here, could mean that what we're actually seeing here is the first real good evidence that the composition of burst is non-baryonic. It's dominated by something else, presumably magnetic field. There are a list of papers listed here if you want, and as I said, this is an ongoing research, so there will be more papers to come, and whoever is interested in joining, just come to me or to Felix and we'll discuss that. Thank you very much for your attention.
Thank you also for a nice review of your works. Questions? Yes, perfect. Stunning.
About the last result for GRE 08, 09, 16C,
yeah.
I think that what you show is that the photosphere is colder than what the fireball model would predict.
Correct.
But it does not necessarily imply that the magnetization is still high in the emission region, because if you have some conversion of magnetic energy into kinetic energy, you can, at the photosphere, be something which looks like a fireball, except that it's colder. in the low monetization.
That is definitely correct. That we had this discussion last week about whether it is possible or impossible to have cold magnetic acceleration. I mean, the caveat here would be if you are capable of accelerating magnetically cold flows. But again, from what my impression was that's not really possible. If you want to have efficient magnetic acceleration, you'll have to hit the plasma. So you'll have to have this hot plasma when it happens.
There is a phase after the electron, the radiation component transfer most of the energy to the baryons until the radiation become optically thin, until the fireball become optically thin. And we've shown this in, other people have shown this, but we worked it out with Ehud Nakar and Rem Sari very carefully in 2005, trying to explain the SGR eruption at the time. Now, during this phase, the photon temperature cooled down. Now, and it's linearly depending on the ratio. The temperature depends linearly on the ratio of when the coupling happens to the end of the energy transfer. Now, with usual parameter, this can be as large as 1,000. And if you take a factor of 1,000, then your discrepancy disappears completely. So this discrepancy that you have that the photosphere is too hot is very strongly dependent on this on some assumptions which are not clear to me that you have demonstrated. So I would be very skeptical on accepting this conclusion that this photosphere of this case is really too hot.
So what I have to say, this is definitely a well-known thing, and this is actually taking into account your SEC that what you refer to implies that from the coasting region to the photosphere, the electron school, and that's why the observed temperature depends as the photosphere gets higher, and the observed temperature really gets lower. That also lies in the heart of that, what we're showing here. There are several models in which we try to look for different values of different radius of the photosphere as a function of gamma. This was actually taken into account.
But it depends also on R0.
Yeah, no.
On R0 and when the acceleration ends.
Yeah.
And if R0 is small and the acceleration ends at 10 to the 9, and the photospheric radius is 10 to the 13, you have enough cooling to erase it completely and to hide it completely. And I don't think that you have shown that this is in this paper that this is not the case.
Well, I hope that you read the paper.
I read the paper.
Thank you. I think. Well, this is a short paper. It's an up-to letter paper, and we didn't just give all the calculations there because of short, but we did them correctly. So we can discuss it later if you're interested. So this is definitely taken into account. Yeah, but you're definitely right. There is a lot of. I said there are some technicalities here that I skipped.
You can't go out with such a dramatic statement, and then you have to be more careful.
Well, that's I'm saying that if you go through this line of reasoning.
I went to the kind of this.
Okay, let's some more questions. Amir?
At this point, I'm too tired, so I can ask the question, but the common wisdom is that during the coasting region it cools, but you can just have shocks during the coasting region and dissipation. So, what do you know? I mean, how do you actually? Why don't you have shocks during the coasting region?
You could have shocks during the coasting region.
So how do you? I mean, you need some model to actually calculate the temperature evolution.
Well, you can. As I said it at the beginning of my talk.
Yes, I missed the point.
You can have, as I said at the beginning of my talk, there are two sources of basically three that you can imagine sources of thermal photons. One is that they emerge from the initial explosion. Second is they emerge from internal shocks that occur deep enough in the flow below the photosphere. There is a certain possibility that one may be able to imagine some dissipation process that produces thermal photon also above the photosphere, but I neglect that. As for the second one, it is possible, and then it really complicates life. So it is not, put it this way, the real how effective this mechanism is really depends on the relative radii of the photospheric radius and the coasting radius, because you cannot have internal shocks before the coasting radius. Okay, so in these models, really, the photospheric radius is not very much above the coasting radius in order to enable this. If I show it over here.
You can,
But yeah, there are some difficulties here that we could discuss.
Okay, let's thank Asaf again.